And I'll now cover what we call the step response of RC circuits. And what do I mean by step? Well, step response means that we will suddenly introduce a new source to the capacitor circuit. And I will use this particular circuit to explain this concept. And in this circuit, what we have is we have a capacitor, and this capacitor is not connected to anything, and it may or may not have some sort of an energy stored in it. And if it does have energy stored in it, that means we can just say that there's some sort of an initial voltage, or we're going to call it V0 across it, or maybe V0. Right? And what happens here is we have the switch and at a certain time, and we're going to call it times T0. What we do is we close this switch. By closing this switch, what happens in here is we connect these to here, and now all of a sudden we introduce the voltage source and the R resistor to this capacitor. And what this voltage source will try to do is try to basically charge or discharge the circuit, but we're going to basically assume that we're going to be charging the capacitor and giving it some sort of an energy. And what we're interested in, it's either finding the current flowing through the circuit, which is a function of time, transient current, and the steady state current as well. And also we're interested in figuring out the V of t, which is the voltage across that capacitor. We can find either one of them, and we can just basically use the capacitor equation, the relationship between the current and the voltage across a capacitor, to find the other. We typically, in RC circuits where we have a capacitor, we target the V, and the reason why is because capacitor is opposed to change in voltage, so mathematically speaking there will be no jumps in the voltage value, and it's just simpler. So let's get started with that. So the way I'm going to analyze the circuit is by simply writing a KVL equation across this loop. So I'll say minus V of S, this is the source voltage, which is a constant if it's DC, and we're dealing with DC circuits at this point, plus I would say I of t times R. I'm assuming that the voltage across it is this one here, and we're going to call it V of R of t, for example. And then here we're going to say plus V of t equals 0. And again, what we're interested in is either the I of t in here or the V of t. So I'll have to write one in terms of the other so that we have equation with just one variable. And I'll choose to rewrite the I of t in terms of V of t because, as I mentioned a few seconds ago, that I'm interested in finding the V of t just because it's simpler. And we typically know from the relationship between the current and voltage in a capacitor that IT is simply C dV of t dt. That's what we know across the capacitor. And of course it has to be plus or minus, but we know that the current is heading to the positive side. That means we're going to have to use a positive in here. So let me just substitute this value in here. What I will get is negative V of S plus RC times dV of t divided by d of t plus V of t equals 0. Okay, I'll do a little bit of algebra just to basically isolate the dV of t divided by dt. I'll basically multiply, or I'll divide both sides by RC, and what I will get is 1 RC V of t equals V of S divided by RC. And this equation is the first order differential equations that describe this step response RC circuit. And this is of the shape, which is dx of t divided d of t plus 1 over tau x of t, and that equals some sort of a constant, and we call the constant kappa, for example. So this is what you see in this particular circuit. It's a first order differential equation that contains our x in this particular case is v. It contains the v of t that I'm looking for and the first partial derivative of v of t, and it also has 1 divided by rc, and rc is tau. As we know, RC circuits tells me that tau is just simply RC. All right, and in this particular case, because it is a step response, what we have is kappa now is not 0. It actually relates to V of S, which is the voltage source that we introduce it suddenly. So now what we have to do is we have to find a solution for this differential equation. And the way I will do it is I'll basically combine the V of t and the dV of t on one side and all the other terms on the other side. So what I will do is I'll say, okay, so that will be, for example, dV of t divided by d of t equals 1 divided by rc, and that will be basically v of s minus v of t. Yes, because we're going to have to move it to the other side. Okay, and then what we have is we can just say dv of t divided by v of s minus v of t, okay, equals 1 over rc. And frankly speaking, I will just basically just say negative in here, positive in here, negative in here, and that basically becomes d of t. All right, all I did, let me just make sure that you're following what I did. What I did is I put a negative in here, I put a negative in here, and positive in here, and that's basically it. So let me just rewrite this one here. So this becomes v of t minus v of s, okay? That's all I did, and I kept that negative in here and negative in here. All right, so we take basically the integral of both sides. So the integral in here, it will be d of y divided by, basically divided by y minus vs, and that will becomes from vt0 all the way to v of t equals negative 1 divided by rc from t0 all the way to t, and that's dt. And again, I did change the variable in here because I want to use v of t in the limits. The same goes in here. I did change, well, this one here, I probably should change it from t all the way to x in here. So I did change a variable because I want to use t in the limit of the integral. So we know that this is simply the logarithm of v of t minus vs divided by, I believe, v of t 0 minus vs equals negative 1 divided by rc, and that's t minus t0. We can also say that v of t0 is just simply the initial voltage 0 here. This is basically this relationship here that we saw, which is the initial voltage. We can easily just call it v of t0. In our cases, is v0 or just v0, basically the initial voltage. That's what we're going to do. All right, so now we take the exponent of both sides. What we'll end up with is v of t minus v of s divided by v0 minus v of s equals e to the negative 1 divided, I can say tau or rc, t minus t0. All right, so what we're interested in is really v of t minus v of s equals just simply v0 minus v of s e to the negative 1 divided by rc t minus t0. And now the final solution, which is v of t, is simply v of s plus v0 minus v of s e to the negative 1 divided by rc t minus t0. And that's basically the solution for that first order differential equation that we found that described what the v of t is equal to. Okay, and this is, of course, for t is greater than or equal to 0. Because remember, the voltage does not change before 0 and after 0, so at 0 it will be exactly the same because it's the voltage across a capacitor and it doesn't change suddenly. Okay, and I think we capture everything in here. So what we need to do is, let's assume that I'm interested now in figuring out the I of t. Just a quick reminder in here, the I of t is the current flowing through that circuit. It's the same current flowing through this capacitor. So we can simply just use this equation to figure out what that current is. And just to double check, we have this one here. The current is going to the positive side. So we're going to be using positive for passive sign convention. So all we have to do in here is just basically say I of t is just simply c times dv of t divided by d of t. So all I have to do is take the derivative of this equation that is highlighted in pink, and I'll multiply c, and then the derivative of v of s. V of s is constant because it's a DC source, so that will be 0, plus, well, what we have is actually negative 1 divided by rc v0 minus v of s e to the negative 1 divided by rc t minus t0. All right, and now we'll multiply both sides, so what we end up with is the following. We will end up with negative r, and that will be v0 minus v of s e to the negative 1 divided by rc t minus t0, and that's for I of t, and that's for t is exactly greater than 0. Because just as a quick reminder in here, this current in here before, like if this switch was open for a very long time, there will be no current flowing through this capacitor right before 0. So I can just simply say the I of 0 minus right before switching is simply 0, but I in 0 plus, actually, we're going to have to go to this equation and substitute t equals 0 to figure out what that is. Basically, I'll have to substitute with this t here equals 0, and I'll get that particular equation and what the value of that equation is. All right, so let me just highlight this one as well. Okay, so now we have the equation for the current and the voltage across the capacitor. We can compute the power if we wanted to, and we can compute anything else. But before we jump to a different, to solve a different example or a different topic, what I want to do is I want to do a few plotting in here. So let me just do a little bit of plotting just to make sure that you guys understand what's happening in terms of before switching and after switching. So what I'll have is I'll basically take this equation in here and I'll try to plot it. And I'll actually write it with this following assumption. I'll assign, basically I'll say that initially V0 is 0. Basically there's no energy stored in the capacitor. It doesn't always have to be the case, but it's just simpler when I'm actually about to draw. And I'll just assume that T0 is just simply 0. And I'll substitute. So that becomes V of T is just simply will be V of S plus V0. Well, we decided that V0 is 0. So that means that here is negative V of S e to the negative 1 divided by RC T, because T0 is 0. Okay, and then we can, of course, you can clean it up a little bit, and we can say it's V of S, which V of S of 1 minus e to the negative 1 divided by RC of T. That's basically the V of T. And the other thing that we can do something similar for I of T, and we can just say it's negative, which is basically V of S divided by R, e to the negative 1 divided by RC and T. All right, so let me just plot these two in here. So I'm going to highlight them in pink in here, or orange. Okay, so let me just do these quick sketching of how do they look like. So let's assume that this is my y-axis, this is my x-axis, and the x-axis will represent time. And initially, I'll basically start with the voltage. So the voltage at 0, so if you substitute this to be 0 in here, okay, so if t is 0, that means the whole thing here is 1. So if you think about it, because this is 1, 1 minus 1 is 0. So technically, right before switching, it will be exactly at 0. And right after switching, it will be also 0. That's what it happens, because I'm not allowed to actually have a jump. And we know that it's 0 right before switching because I told you initial voltage is 0. Then what happens? Well, what happens, as you will see, we have some sort of a transient source. So if t goes all the way to infinity, for example, so the whole term in here becomes 0. This becomes 1. So I'll end up with just V of S. So eventually, what I'll have is I'll have V of S. And this one here is actually, it will reach it exponentially speaking. That's what will happen. That's a voltage across that capacitor. And that makes sense because if you take a look at this, what we did is we have a capacitor that is not charged, and all of a sudden we connected it to a source, and that capacitor will get all the voltage Vs eventually, like after you wait for a very long time, specifically 5 taus or 5 time constants. All right, then how about the current? Well, the current in here, it used to be 0, okay, before, and I'll just basically do that in pink, for example, in here. So it used to be 0 before switching. We know it's before switching because there's no current flowing through that capacitor. But then at t equals 0, if you substitute this here to be 0, so the whole thing becomes 1, you'll end up with Vs divided by R, which is some sort of a value here, Vs divided by R, and you'll see that the current actually jumps, and the current is allowed to jump between 0 to 1 because it's between 0 to some sort of a value because it's a capacitor. It opposes a change in voltage, not current. The current is okay. And then eventually you will see that if t goes to infinity, for example, the whole term goes to 0. So the whole thing goes to 0, and the current in here basically slowly basically reaches 0. That's what happens in here. So that's in terms, this is basically the current, and the one in here is just simply the voltage across the capacitor. And the other one is the current across that capacitor. And it makes sense. It actually, if you think about it in here, what we did is we closed the switch, the capacitor got charged, and once it reaches a certain value, that's it, the current actually stops and it acts as an open circuit. That's what we have.